Let's talk about improper integrals. In this video, we're talking about the second type of improper integrals, so we're in part V, and these are the sneakier ones. So you can see here the example that we're going to do in the video. I have the integral from 0 to 3 of 1 over x minus 1 squared. So this is sneaky because infinity is not one or both of the limits of integration here. So it doesn't really look like it's an improper integral, it just looks like a normal integral. But let's kind of pause for a minute and think about what the function in there actually looks like. So I'm looking at f of x equals this formula here, 1 over x minus 1 squared. So you may not just immediately come up with what it looks like per se, but we can kind of put a few things together and get a good enough visual. So I can tell that I cannot plug 1 in, right? 1 is the only thing not in the domain of this function. There's no cancellation here, so I have a vertical asymptote at x equals 1. That's because plugging in 1 would make my denominator 0, and there's no cancellation to take away that issue. Alright, so I have a vertical asymptote at x equals 1, so I'm going to kind of draw that in here. Because this is 1 over something squared, all of my outputs are always positive. So this kind of gives me a sense of what the function is doing around that asymptote. And really knowing this much is not, like this is kind of extra, we don't need to have the visual this specific. The vertical asymptote location is kind of the more important part here, but if we consider that it's always positive, it must be going up on both sides of the asymptote. And in fact, this function looks sort of like this. So what we're doing if we're integrating from 0 to 3 is computing this area here. This is x equals 0. So we have infinite area here, up, 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 up forever. So that may come out to be some concrete finite number, or it might just be infinity. It kind of depends on the function. So we've got to do some more work to decide. And then if we go all the way to 1, 2, 3, we'll stop here. So we're doing other area here, and again going up, 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 up. May come out infinity, and it may come out a number. Okay, so now that we've identified that there's a vertical asymptote smack in the middle of the interval I'm considering, that means that this is an improper integral, and in fact it's the most annoying kind, where I have to actually split it and like acknowledge the problem area at 1. So that's my first step, is I'm going to write this as the integral from 0 to 1 plus the integral from 1 to 3. So I'm considering it two separate improper integral problems, and I'm splitting it at 1 because that's where the asymptote is, so each of these are going to kind of highlight the issue. So each of these are two little improper integrals, so I'm going to write them with a limit for the 1 in each spot. So this one will put a variable here and then limit that to 1, and then this one will put a letter here and limit that to 1. Alright, so we'll do this one, I'll say 0 to b, because usually it's a and b if we're using letters. So I'm going to have b approach 1, and because we're coming just from the left side of 1 for this piece of it, I'm actually going to say just 1 from the left. That's actually not really going to affect my final answer here, but it is technically correct. And then we'll keep everything else the same. And I'm going to do something very similar here. So I still have 3 as my upper bound here, but instead of the 1, I'll put an A as my new letter, again, just because it's usually A and B if they're letters. And then we'll have A approach 1, but this time it'll be from slightly above 1, which again won't actually affect our answer, but should be included every time, just in case it does. And then we have that same function. Okay, so now our next several steps are just integrating. These limits are just going to kind of track down with us for a while, and our very last steps will be to evaluate each of those limits. Okay, so we do have two separate problems here, but they're going to use the same antiderivative. So let's think kind of quickly here about integrating 1 over x minus 1 squared. They both need this antiderivative. You could think of it as a u substitution, u equals x minus 1. It's a very simple u substitution, du is dx. And what you'll get is 1 over u squared, aka u to the negative 2. So we're going to get 1 over negative 1, u to the negative 1. We don't need the plus c here because we're about to plug stuff in. So if we simplify this, we have negative 1 over u. So that'll be negative 1 over x minus 1 if we plug that back in. So this is the antiderivative I'm going to use in both spots here. Okay. So like I said, I'm going to carry this limit notation down and say, okay, this is negative 1 over x minus 1 evaluated from 0 to b, and we're just sort of treating b like a number, plus the other limit here, same antiderivative, evaluated from a to 3. So now in each of them, I'm going to plug in the top bound, plug in the bottom bound, and subtract. And then we'll be in a place where we can evaluate the actual limit. Alright, so let's just focus on the one on the left here. So I plugged in b for x, and then I plugged in 0 for x. This has a lot of minus signs going on, but this is going to be negative 1 over negative 1 is 1. So this is just something minus 1. And we're going to worry about, of course, the limit part here, right? This should always just come out to be some number, which won't affect our final answer in terms of converge or diverge. This is where kind of the action is happening here. Now, as b approaches 1, my denominator is clearly approaching 0. So I just have negative 1 divided by teeny, teeny, tiny numbers. This limit doesn't exist. We could get more specific here because b is approaching 1 from a specific side. We could say one of the infinities for both, but the same thing is going to happen over here in a minute too. But this is one of those cases where you don't need to specify. As long as it's some kind of DNE, you know what your final answer is going to be, which is that this improper integral diverges. That's the entire answer. If either, so what we did was break it up with that vertical asymptote in the middle. So if either one of these pieces or both comes up DNE from the limit, you're going to say that the integral diverges. And in fact, you get kind of a similar situation here where this also comes out to DNE. If the improper integral is going to converge, this limit would exist and this limit would exist, so you would actually get like a number out instead, and you can actually compute a final number. So what you would have said in that case is, okay, it converges and it equals, you know, whatever that final number is when you add it all up. But for us, our final answer here is that this sneaky improper integral diverges, so the red area and the purple area really are infinite.